Hello everyone and welcome to the Algorithms. In this video, we are going to talk about the TARJANs algorithm for finding strongly connected components in a directed graph. After the discussion, we would also look at the code on how to actually come up with a working solution. I would highly recommend you to go through the video and our contents in the website thealgorist.com on the articulation points, and that would highly help you to understand our discussion here, because we will be using a lot of concepts introduced in the articulation points like chapter. Specifically, we will be using the concept of um, the discovery time and the earliest discovered node reachable. In the chapter, the articulation points, we had also shown how the algorithm is actually derived. So in this chapter, we won't go through all those exercises and discussions. We would assume that you already know the foundational basics of the Tarjan's algorithm, and we will just show that how the Tarjan algorithm helps us to find strongly connected components in a directed graph. So let me show you how you can access the contents um, on the articulation points. So all you need to do is go to the algorithms and data structures link, and there you can see that we have a series on Tarjan's algorithm, and the very first chapter in that series is articulation points. Um, so please go through the chapter and also watch the video, and then come back to the strongly connected components. So what is a strongly connected component and a strongly connected graph? A strongly connected graph is a directed graph in which all the nodes in the graph are mutually reachable from each other. Some of the examples are given in this diagram. So obviously a single node, a graph with just one node, is considered as a strongly connected component because there is only one node, and that node is obviously reachable from itself. So all the nodes in the graph are reachable from each other, and in this case we have only one node. Then, and in all other graphs, we can see that all the nodes are reachable from each other. There is at least one path from every node to all other nodes. um, Also, an observation here is that the connected components are cyclic. Now let's talk about strongly connected components in a directed graph. So a graph can have one or more strongly connected components in it. And when I say graph, I am always referring to directed graphs here. So let's look at the first graph. We see that the first graph has two strongly connected components. 1, 2, and 3 form a connected component, I mean a strongly connected component, and 4, 5, and 6 form another strongly connected component. If you look closely at each of these graphs containing one or more strongly connected components, you would see some very important characteristics of strongly connected components in a graph. The first one is, if you see, for every strongly connected components, there is no way that you can get out of the component and then again come back. Like, you can get out, but there is no way you can actually come back. We know that the Tarjan's algorithm is based on constructing a DFS spanning tree. The algorithm to find the strongly connected components in a graph is based on identifying two very important situations here. To discuss the first situation, what I will do is I will remove the edge that connects F from D, because that will be the second situation that we will be discussing. So let's say we have the given graph like this, and let's talk about this strongly connected component. We see that when we do a DFS while forming our DFS spanning tree, the only entry point to this strongly connected component will be E. So E is the root of this strongly connected component. And since this is a strongly connected component, all the nodes are connected to each other and to no other nodes outside of the strongly connected component. So the earliest discovered node that will be reachable from any node in this strongly connected component will be whichever node is the root of the strongly connected component. Now, if you think in general, the root of the strongly connected component, like which is the entry point, all the nodes in the strongly connected components will be discovered after the entry point of the strongly connected component. So they will have discovery time greater than the discovery time of the entry point, and I am calling that entry point the root of the strongly connected component. And so the root will be the node which is the earliest discovered node reachable from any node in the strongly. Now you might say that the root of the strongly connected component, which is the entry point of the strongly connected component, that node can have an outbound edge which connects it to some subgraph of the given graph. And you might say that through that outbound node of the entry point can reach some node which has lower discovery time than the entry point itself. Now let's talk about a back edge. Let's see if this outbound edge can be a back edge or not if this node happens to be the entry point of the strongly connected component. So I will add one dummy back edge to show that any outbound node from an entry point of a strongly connected component cannot be a back edge. So I will show you how. So let's take a back edge. So first of all, we said earlier that one of the characteristics, or I would say one of the very important observations about strongly connected components, is that there should be no way that you go out and then again come back. You can go out, but then you would see that there is no way you are able to come back to the strongly connected component. So here we would see that that does not hold true. So we have this, we just added this back edge. So now we are at E. So from E we are able to go to A, and then we are again able to come back to E. And we also now see one interesting thing here, that uh, now the strongly connected component also includes A. If you see A, E, G, F, then back to A, from any node in this component, you can go to any other nodes, which nullifies our assumption that E is the entry point of the strongly connected component. Because now, after adding the back edge, this is our strongly connected component, and A happens to be the entry point, and everything discussed about the strongly connected components now holds true for this AEGF strongly connected component. You see, from A there is no way you can go out to some other component of the graph and then again come back. Like, you can go out because there is a node from A to B, but there is no way you can come back to A, B, like, because there is no node from B to A. So so now back to the initial point of our discussion. For any um, entry point of strongly connected components, the entry point will not have any back edge. So that is why we cannot have this back edge here, because that does not keep E the entry point for the strongly connected component. And when we are computing strongly connected components, we try to find the maximal strongly connected components. Like, if we have a back edge from E to A, it's true that EFG is still one strongly connected component, but we compute the maximal strongly connected component. So we also need to include A in that strongly connected component as well. Because if you think, each node is strongly connected component on its own. So we don't compute just any strongly connected component, we compute the maximal strongly connected components. If there is a smaller connected component, but it is a part of a bigger strongly connected component, then we need to output the bigger strongly connected component, to which the smaller strongly connected component is just a subset. So if we had this back edge, then the strongly connected component would have been AEGF and not just EFG. And in that case, A would have been the entry point for these strongly connected components. So very important characteristic of strongly connected component is that the entry point will not have a back edge. So a strongly connected component cannot have a back edge for the entry point, for the root of the connected component, when we do our DFS on it and construct the spanning tree. So one observation is root of strongly connected component does not have back edge. Um, so now you might say, yeah, so we saw that if a component is a strongly connected component, then in the DFS spanning tree, the entry point for that strongly connected component won't have a back edge. But what about cross edge? It can have a cross edge, right? And that is exactly what we will discuss for our next scenario. So for this scenario, the focus of our discussion is that what would be the lowest discovered node reachable from the entry point of the strongly connected component in the DFS spanning tree. So the entry point is the node E in this case. So what would be the earliest discovered node reachable from E? So if it cannot have a back edge, it definitely cannot reach a node for which the discovery time is less than that of the entry point of the strongly connected component, which is the node E in our case. So a very important observation we just made is that for the root of strongly connected component, lowest earliest discovered node really reachable, and we would write here a lowest node. We would denote that by lowest node here. So the lowest node for the root will be same as the discovery time of the root, because the root of the strongly connected component itself will be the earliest discovered node that can be reachable from the root, which is also the entry point of the strongly connected component. And that is because we just proved that if this is if the current component we are in while doing the DFS, if the current node happens to be the entry point of the current strongly connected component, then that node cannot have a back edge. And if the node has a back edge, then that is definitely not a root of a strongly connected component. So we just got a formula here, a condition that we should check for every node, that whether the lowest node reachable from that node is equal to the discovery time of that node itself, whether it is true or not. If it holds true, then definitely it is root of strongly connected components. And how we find the strongly connected components, that we will discuss after discussing these two scenarios. So this covers the first scenario. Now we will be discussing about the second scenario, which is about the existence of cross edges in strongly connected components. Any node which is a part of a strongly connected component can have one or more cross edges. That is perfectly fine. But there is one very interesting observation about that. So we know that E is entry point of the strongly connected component EFG. Now let's take a cross edge from E, and let's see what observation we are making here. So I just took one cross edge and I connected that to a new node, say H. What can you say about H? That H itself is a strongly connected component. Now, how about you connect E to any other node in the graph, as long as E does not violate any of the rules that need to be maintained by the root of a strongly connected component. So let's connect with D. What observation we can make here? The interesting observation here is the cross edge is again connecting the node of the current strongly connected component. So the current strongly connected component is the strongly connected component EFG, and from that strongly connected component we have a cross edge which connects the strongly connected component EFG to the node D, and we see D is again a part of another strongly connected component. So the observation we can make here that any cross edge from any node of a strongly connected component will connect it to another strongly connected component, and we know that any node, any like single node is a strongly connected component as well. So it will connect to some strongly connected component. So whenever we encounter a cross edge, we just need to ignore it, because cross edge takes us to a node which has already been visited, and we just showed that the node that the cross edge will take us to will be a part of a strongly connected component, which means a cross edge will always take us to a strongly connected component which has already been visited and processed. So don't worry about that. If you get a cross edge, just ignore it and continue. And in the code we will see how we are detecting the cross edge. So our second very important observation is, if cross edge found, just ignore and continue. Now we have a third scenario here. What we have a forward edge from any node of a strongly connected component. Now we know any node that is reachable through a forward node has a discovery time greater than the current node. So a forward node will not give us a earliest node, like discovered node reachable from the root of a strongly connected component, because any node in the strongly connected component which has a forward node, it will just take us to a node with a discovery time greater than the discovery time of the root of the strongly connected component. So we have here two forward edges here, and we see that they don't affect the earliest discovered node reachable from A. So in summary, we just need to handle two scenarios in our algorithm. The forward edge, like any forward edges in the graph, is not a problem. So we don't need to handle any forward edge separately. But we do need to check for cross edge to make sure that that is not affecting the earliest reachable, the earliest discovered node reachable from a strongly connected component. So the first thing that we need to check is whether an edge is cross edge or not. And the second thing we need to check for any node if the earliest discovered node reachable from that node is equal to the discovery time of that node or not. Next, we will be discussing how we will actually keep track of the nodes in a strongly connected component. For that, there is a very easy and intuitive way. Say we can take a stack. So in like while doing DFS, whenever we visit a node, we push that node immediately. So let's talk very specific to a strongly connected component. So for EFG strongly connected component, we know the entry point will always be E. There is no other way while doing DFS we can reach the strongly connected component. So say we already have earlier discovered node in the stack, and now we reached E. So the first thing we do is we pushed E in the stack. From E we reach F and we visit F, we put F. From F we go to G, we push G, and from G we go to E, but we see E is already visited, so we backtrack to F and then we backtrack to E, and for every edge we are checking this condition that whether the earliest discovered node reachable for the current node is equal to the discovery time of the current node or not. So we are checking for this condition for every node while doing the backtracking. So from G to F, while we backtrack, we checked for G and we saw that this condition was not met. While backtracking from F to E, we checked for F and we saw that this condition is not met. Now we are at E and we need to backtrack from E to whichever like node is um, next to E in the stack, and we check for this condition and we see that this condition is met for the current node. So we know that E is root of a strongly connected component. And now you can see it is very easy to if you want to just print those like all the nodes in that strongly connected component, it's now very easy to process that. So you go on popping from the stack till you find that the current node is the top element in the stack. And since the current node is part of the strongly connected component, the same strongly connected component, in fact, it is the root of that strongly connected component in the DFS spanning tree, you pop that one as well. So here, so when we are at E and this condition um, was met, we popped G, we popped F, we popped E. So we went on popping um, till we found the current node in the stack, and we popped the current node from the stack as well. So we see it's very easy. So this is how we will keep track of the elements of the strongly connected component. Now we will do a dry run of the algorithm we just discussed, and we will test if the approach we discussed actually produces the correct result or not. So I will modify this graph little bit to better demonstrate the cross edge scenario. So I will disconnect this edge and I will put an edge between D and F. So we see here something interesting that is on stack that will actually help us to identify if an edge is a cross edge or not. Let's start our DFS from A, and you can do DFS from you can start your DFS from any node in the graph. It's just my choice to start from A. So let's visit A. The discovery time becomes 1, lowest node is initialized as same as the discovery time, which is 1. We push A on stack, and on stack becomes true. From A we can either go to B or E. Let's go to E. Discovery time becomes 2, lowest node becomes 2. On stack we will put E on stack becomes true. From E we can only go to F. We go to F. For F we put all the entries. We put F in the stack. We make on stack true for F. Next we go to G. Discovery time 4, lowest node 4. Put G on stack becomes true. Now this is where we would be using a lot of concepts we have introduced in the articulation points video and the articulation points chapter in the algorists.com website. That is, now from G we can only go to E, and E is already visited. So, and there is no other adjacent edge of G. So now we need to backtrack from G to its parent, which is F. But before backtracking to F, we need to see if we are getting a lower earliest discovered node reachable from G or not. So G has only one adjacent edge from through which it can go to, it can reach node E. So we go to E, and since E is one of its ancestor, and we have very um, clearly discussed this in the articulation points chapter, and we have discussed in depth that when we compare with any of the ancestors, we compare with the discovery time of the ancestor and not the lowest discovered node reachable from the ancestor. And we also know why. Because we talk about the back edge, that we can have only one back edge, and all these are explained in details in the articulation points chapter and the video. So we compare the earliest discovered node reachable from the current node with the ancestor. So the current node is G here, ancestor is E. For G, the current earliest discovered node reachable is the node with discovery time 4. For E, we see it is 2. We take the minimum. So the minimum of 2 and 4 is 2. So we update the earliest discovered node reachable from G to be the node with discovery time 2. And then we backtrack to F. Now we are at F. We compare the current earliest discovered node reachable from F, which is 3. Um, we compare with the earliest um, d- discovered node reachable from G, and we see that for G it is 2, so we take the minimum and we make it 2. Now from A, and why we did not compare with the discovery time of G, because G is not an ancestor of F. In fact, G is a descendant of F. We discovered G after we discovered F. So for any descendant, we compare with the earliest discovered node reachable and not with the discovery time. We only compare with the discovery time if that node happens to be the ancestor node of the current node. So now we are backtracking to E from F. So E has only one edge, adjacent edge, it goes to F. So for F, we see that the earliest discovered node reachable is 2, and the current earliest discovered node reachable from E is 2, so we take the minimum, so it remains the same, which is 2. And now we see that the discovery time and the lowest reachable node happens to be the same. Both are 2, which means E is a root of a strongly connected component. So what we need to do is we need to go to the stack and we need to go on popping um, till we find E on the stack, and then we pop that as well and stop popping. So we pop G, so the first strongly connected component we are getting as G, we are marking G as false on stack, because G is not in the stack anymore. We popped F and we printed F. We made on stack as false, and then we popped E, and E also happens to be the current node, so we popped E and we stopped popping, and we marked E as false for on stack. So now we are back from E to A, and then we visit the other um, node, the other adjacent edge of A. But before that, should we check for the condition whether it is a root or not, or a root of, like whether it is a root for a strongly connected node or not? The answer is no, because we are not done visiting all the adjacent nodes for the current node, which is A. So we check for the condition only like when we are backtracking from the current node after visiting all its adjacent nodes. So since doing a DFS on A is not complete, since B, which is one of the adjacent nodes of A, is still left for visiting, we won't be checking for the condition to see whether it is a root of a strongly connected components or not. So next we visit B. The discovery time of B will be 5. We initialize the earliest discovered node reachable as 5. We put true for on stack. From B, and we definitely put B in the stack. From B we can go to C. We do the same thing for C. We put the C in the stack, and then from C we go to D, put the D on the stack. Now is now comes the interesting part. From D we can either go to B or F. Now from D, let's go to B first. We see that B is already visited, so we don't do our DFS again on B, because then it will be an infinite process, like non-terminating process. So, and that is what we do, do in DFS. We don't do a DFS on a node which has already been visited. So we go to D, we then go to B, and we see that B is visited, so we don't do DFS on B. But before backtracking, we will check the lowest discovered node for B. But since B is an ancestor, and because it has been discovered before D, we will be comparing with discovery time of B and not the earliest discovered node from B. But that we will do before backtracking to C. So let's visit the other adjacent edge we have. So the other adjacent edge of D is the edge D2F, and this is a very interesting edge here. As we have already discussed, DF is a cross edge because it goes to a node which is already visited. So how can we distinguish between the cross edge and the back edge D to B, the edge D to B? So what distinguishes the node where the current node reaches through cross edge and back edge is that the node where the cross edge takes the current edge to a is a node which is not only visited but also processed. So if is not only visited, it has also processed, and we know by looking at the stack operations we have done, we see that we have popped f from the stack because we have already processed f, whereas b is still on the stack because we have visited b but we are not done processing b. So in general, um, when we work with back edge and cross edge while doing DFS, we generally keep two states. One is visited, another one is visiting. So here, the the state processed is equivalent to the visited process in the visited state in the like general DFS. So in a general DFS, what we can do is when we visit a node, we mark that as visiting, and then only mark that as visited when we are done doing a DFS on that node, which means when we are done doing DFS on all the adjacent nodes of the current node, then we mark that node as visited, and we make visiting as false again. So here uh, we know that uh, our node is being connected by a cross edge when we see that the node has already been processed. That is, the node has not only been visited but also it has been processed, and we know that by looking at the stack. If a node is in the stack, we would know that that node has been visited but not yet processed completely. But if a node is visited but it is not in the stack, then we know that that node has already been completely processed, and any edge that is taking us to that node is a cross edge. Um, so that is why we need this variable on stack, or we need to keep a data structure for on stack boolean, so that we know whether a node is on the stack or not. So now we are back to where we were in our DFS. So we were in this edge which was leading us to f, and we see that for f it is in visited state, but for f we also get false in the on stack. So that is how we know that the current um, edge is a cross edge, and we just ignore. So we have processed all the adjacent edges of D, and now we are ready to backtrack to its parent C. So now we should update the earliest node reachable from D. So we see that there is an adjacent edge which is actually a back edge taking the node to B. So we compare with the discovery time of B, and we see that the discovery time of B is 5, whereas the discovery time of D is 7. So we take the minimum and we update the earliest discovered node reachable from D is the one with the discovery time 5. Now we are back to C, and we see that all the adjacent edges of the C have been processed. So we update the earliest discovered node reachable from C. We see that the adjacent node D has earliest node as 5, and we have 6 for C. So we take the minimum and update it to be 5. Now we are back to B, and we see that all the adjacent edges have been processed. we see that its adjacent node C has earliest discovered node reachable as 5, and the current earliest node reachable from B is also 5, so this keeps unchanged. And now we see that the discovery time of B is same as the lowest node reachable from B, and this is the condition for a node to be a root of a strongly connected component. So we know B is root of a strongly connected component. So we go to the stack, we pop 7, we see that 7 happens to be the discovery time of D, so we mark on stack as false, we print D, and then we pop the next top element, which is 6. So 6 is discovery time of C, we print C, and then we are at B. B is also the current node, so we pop B and we stop the popping process here, and we print B. I just noticed that for the last strongly connected components I had missed the E here, so I also need to add E. So now from B I'm backtracking to A. I see that all the adjacent edges of A have been processed. So I check for the lowest node reachable from A. I compare with B and E because though like those two are the adjacent nodes. For B, the earliest node reachable has discovery time of 5. For E it is 2, but I have a lower earliest discovered node reachable, which is 1, so I don't change this one. And now that all the adjacent edges are processed, I check if this is a root of a strongly connected component or not. We see that it meets the condition for that. It because it has the same discovery time and the earliest discovered node reachable. So we go to the pop, we go to the stack, we popped A, we printed the strongly connected component, and we updated on stack as false for A. Now a very interesting observation. So while running our algorithm to find the strongly connected components in the given graph, we got the strongly connected component GFE first. We discovered this one first, then we discovered DCB, we discovered this one second, and at the end we discovered A. If we just represent the strongly so if we represent the graph just using strongly connected components and not using all the nodes, how would we how will the graph look like? So say strongly connected component A, strongly connected component B, C, D, and strongly connected component E, F, G. So the graph will look like this. Strongly connected component A is pointing towards strongly connected component B, C, D, and strongly connected component E, F, G, and then strongly connected component B, C, D has one edge to strongly connected component E, F, G. So what would be the topological sort of this graph? So we see that strongly connected component EFG has dependency on both strongly connected component A and strongly component BCD. So strongly component EFG would definitely come at the end of the topological sort. Then I see strongly connected component BCD has dependency on strongly connected component A, and strongly connected component A has no dependency on any other strongly connected components. So in the topological sort, strongly connected component A will come first, followed by strongly connected component BCD, and then strongly connected component EFG at the end. And in which order did we actually discover the strongly connected components? We discovered EFG first, which is here, followed by BCD, which you can see here, and then at the end we discovered A. So it is a very interesting relationship between the order in which we discover the strongly connected components in a given graph and the topological sort of the um, graph in which we would only have the strongly connected components. And the relationship is that we discover the strongly connected components in the reverse order of their topological sort. And if you recall how you can implement topological sort using DFS, there also you would see that we use a concept of the sync vertex, and we discover yeah, we process the node that comes at the end of the topological order first. So we put in the resultant set the node that comes at the end of the topological order, and we put the node that is the first that happens to be the first in the topological order. We put that at the end of the result set when we do a topological sort using DFS. So when doing DFS, we get the same thing. We get the nodes in a order which is exactly the reverse of the topological order. So it is not a surprise that similar thing is happening here, because here also we are using DFS to and we are creating the DFS spanning tree. So so yeah, this is really interesting. And if you want to learn more about the topological sort and how you can do that using DFS, feel free to go to the website, the algorithms.com, and then go to the algorithms and data structure, and then from there you need to go to the graph theory select series, and there is I can see yeah, there is the chapter, the fourth chapter is topological sort. If you go here, everything is discussed in details how you can do topological sort using the DFS, BFS. You can see detailed discussion here. If you go to the chapter for the TARJANs algorithm to find the strongly connected component, there you would find the working solution for this algorithm. So I will walk you through the code. So this index is nothing but the discovery time, the count to count how many strongly connected component the given graph has, and then this is the method that will be returning all the strongly connected components, and the type is of lists of integers. So we would have each connected component as a list of integer, and then list of list will contain all the strongly connected components. And so basically from here, we are calling the DFS method, which will actually do um, all the processing that needs to be done. And this needs to we need to call DFS on all the unvisited node. This is important because this is a um, directed graph, so just in one pass all the nodes may not be visited. So we actually need to have this for loop on all the nodes of the given graph, and for each of them, if it is not visited, which we can track um, by looking at the discovery time, because the discovery time starts from 1, but initially it is initialized with 0. So if we see that the discovery time is 0, that would mean that that node is not visited and processed yet. So let's go to the DFS method. So DFS method takes the graph, and we have the concept of ID here. So how what I'm doing here, I am assigning each node an ID, and the ID represents to which strongly connected component it belongs to. So if say there are there are 3 strongly connected components, then we can give IDs to each of them, and for whichever node belongs to whichever strongly connected components, we would just assign the ID of the strongly connected component to that node. Then we have the discovery time array, we have the earliest discovered node visible array, we have the stack to keep track of the nodes in the current strongly connected component. So basically this is the node from where we will be popping all the top nodes when we find a root for our strongly connected components, and we will go on popping till we get the root on top of the stack, and we pop that as well and stop the popping for that current strongly connected component. And we have already discussed all this. On stack is for detecting the cross edge, and it should be commented here. Yeah, you can see on stack to handle cross edge scenario, which we have already discussed. And then obviously we have the current node on which we are doing the DFS. So the first thing we do is we increment the index, and we assign that to discovery time and earliest discovered node for the current node. We push that on the stack, and we make on stack true. Then we iterate on all the adjacent edges for the current vertex. So we iterate over all the adjacent vertices for the current vertex, and if we see that the adjacent vertex has not been visited yet, we do DFS on that. And after that DFS on the adjacent vertex is done, we compute the earliest discovered node reachable for the current node. So since this adjacent node was not visited, this is definitely not an ancestor. So we compare the current earliest discovered node visible from the current node, and the earliest discovered real node visible for the adjacent vertex, and we take the minimum as we have already discussed. Now comes the scenario where the adjacent node is already visited. So either the edge which is leading us to this adjacent vertex can either be a back edge or a cross edge. If it is a cross edge, we should ignore it and continue. So if it is not on the stack, that would mean that this is a cross edge, so we just ignore and continue. But if it is an ancestor, then we just check the discovery time of the ancestor and we take the minimum of that and the earliest discovered node reachable for the current node that is computed till now. We take the minimum of those two, and after we have done DFS on all the adjacent vertices of the current node, we check if the current node is the root of any strongly connected component or not. So we check if the earliest discovered node really reachable for the current node, if that is equal to the discovery time of the current node. If that is true, then we know that we got one more strongly connected component, so we increment the count, and then we pop from the stack and we assign the node, the top node we just popped, we assign the strongly connected component ID to the same as the count. So so that is how we are like assigning ID to the strongly connected component. So count is initialized with 0, so the and we whenever we find a strongly connected component, we increment that by 1. So the ID, so if there are n number of strongly connected components, the ID would be 1 through n. So we assign the ID to the node there. That is how we would know that this node is belongs to this strongly connected component. And we also make on stack false for the node we just popped. So yeah, this is the working solution for the algorithm we just discussed. And we also have test cases here. We have tested on this given graph, we have tested on this graph, and we have tested on this one. It was great talking to you about the TARJANs algorithm to find strongly connected components in directed graph. Do let me know if you have any questions or doubts through comments or email, and I'd be more than happy to clarify any doubt you might have. And also do let me know if you want me to write a chapter or make a video on anything specific that you would be interested in knowing more. So I would see you in the next video. Till then, take care and stay safe. Thank you.